Okay, so in the previous lecture we have seen how to plot the Bode magnitude plot, and in this video we will see how to sketch the Bode phase plot. So in the Bode phase plot we only have to consider three things. One is the S term, second is the S plus A term, and third is the quadratic. So there is no role of the gain k value in the Bode phase plot. In the Bode magnitude plot we have seen that that decide our origin, but in the Bode phase plot it don't have any role. So we will only see these three things. So let me just explain these one by one. So S term. So one S term contributes to 90 degrees, plus minus 90 degrees. So suppose we have the transfer function h of s, and we have s cubed by s5, and there are three zeros at origin, so 90 into 90, 90 plus 90 plus 90, so we'll have 270 here, okay, divided by s5, so 590s mean 450, and they are in the minus because they are poles, right? So if we add these two, we'll have minus 180 degree. So this decides the origin of the phase plot. So our origin of the phase plot will be at minus 180 degrees, right? And we will draw the rest according to it. Minus 135 degree, minus 90 degree, and similarly minus 225 degrees, similarly minus 225 degrees, minus 270 degrees. So it only decides the origin of the phase plot. So let's say we have in the transfer function h of s, we have only a single 0 here, and we don't have any s term in the denominator. We only have a single 0, right? So 90 degree contribution from the numerator, 0 degree from the pole. So our origin will be at 90 degree, and then 135 we will draw the rest with 45 degrees gap, right? Plus 45. Okay, so this S term only decide the origin. We'll just, like, for each pole and 0 we will just write 90 or plus minus 90, and we will add them together, and whatever the value we get, that will be our origin, right? For the next term, the S plus A term, so in the Bode magnitude plot, for the S plus A we draw a straight line until we hit the break frequency, and we move either up or down depending upon either it's a 0 or a pole. For 0 we move up, for pole we move down, and this line go till infinity, right? In the Bode phase plot we will go straight just like we did in the Bode magnitude plot, but this time we will move down like this or up like this, but it will have at certain value it will go straight. It will go straight, not it will not go till infinity like in the Bode magnitude plot. So it will straighten out, right, at some particular value. So I'll explain how. So let's say we have the break frequency s plus 5. Firstly, let's say s plus 1. Okay, so as in this plot you can see there are basically 2 points. One is the starting point and the other is the ending point. So we have to decide what will be the starting point and what will be the ending point of the slope for each break frequency, right? So for this break frequency, the starting point will be its corresponding point in the previous decade. So it's 1. So we know that our points are 0.1 in the log scale, 1, then 10, then 100, then 1000. So if we have a 1 here, so the previous decade value is 0.1 corresponding to 1, right? And the next decade value is 10. So our plot will start at 0.1 and ends at 10, right, for the break frequency of 1. So if our break frequency is 10, then the plot will start at 1 and ends at 100, right? But if our break frequency is, let's say, somewhere in between here, 5, then our plot will start at 0.5, because previous decade value is the central value of these 2 points, like 0.5. So it will start at 0.5 and then ends at the next decade central value, which is 50. So I hope you understand this point. So if it's a single pole, like I mean the multiplicity is 1, then its slope will be minus 45 degree per decade. And we know that this line travels 2 decades, because if it start at 0.5, then it will reach till 5 at minus 45 degree per decade, and then it will end at 50. I said that for 5 break frequency, it will start at the previous decade and ends at the next decade. So it travels totally 2 decades. So it will travel a total distance of minus 90 degree, right? But at minus 45 degree per decades. So it travels 2 decades at the slope of minus 45 degree per decade. And if it's 0, then it will be plus 45 per degree per decade, and if its multiplicity is 2, then it will be plus minus 90 degree per decade. So for 0 it will be plus 90 degree per decade, for pole it will be minus 90 degree per decade. And the same concept will be with for the s square plus, for the quadratic term, because we know that we know how to calculate the break frequency for the quadratic term. So we will calculate the break frequency exactly by the same way that I have explained in the previous lecture. So you can watch that video again if you don't know how to find the break frequency. So once you obtain the break frequency, just draw a line from the previous decade corresponding to that value, start drawing the line, the slope with plus 90 degree, because for the multiplicity of 2 plus 90 degree per decade. So it will total in 2 decades it will total travel a distance of 180 degree, right, with a plus 90 degree per decade if the multiplicity is 2. So this is the whole theory, whole concept behind the Bode phase plot. Now let's just draw the Bode phase plot for this question. So we have calculated that we know the first thing that we will do, we don't need to bother about the value of gain k. So because it doesn't matter whatever the value of k in the phase plot, we have to find where our origin is. So our origin is, we have only one pole at the origin, we don't have a 0 at origin. So there will be 0 degree contribution in the numerator, and there will be minus 90 degree. I told you that one pole or 1 0 correspond to 90. So there is no zeros, so 0 degree. There is one pole, so minus 90 degree. If it was 2 poles, then it will be minus 180 degrees, and if it was 1 0 also, then I have explained before that how you have to just add them, and whatever is the total contribution, that will be your origin. So now our origin will be at minus 90 degree, right? So we will draw the phase plot according to this. So this is our origin. So the upper value will be minus 45, then 0, and lower will be minus 135, and like this, right? The other two break frequencies, so I have described earlier that how to find them. So we have calculated them as omega 1 is equals to 10 for these zeros in the previous lecture. So it was omega 1 is equals to 10. So this was the break frequency, because we have taken this 100 out, and this was in the denominator then, and we have omega square in the denominator. So omega square is equals to 10, and then we obtained omega is equals to 10, right? So this is our first break frequency, and we know that its multiplicity is 2. So its slope will be plus 90 degree per decade, okay? And we have the second pole, this is the pole, and its break frequency is 10 power 4, and its multiplicity is 1. So it will be minus 45 degree per decade. So we have to handle only these two break frequencies, and this decided our origin, and these two are the only left break frequencies. So let's just start plotting this. So our origin is at minus 90 degree, upper value is minus 45, then we have 0 degree, then we have 45 degree, then we have 90 degree. So in the phase plot, as it is a phase plot, so we will have degree here and we will have omega here, right? So we can start it from 0.1, 1, 10, 100, 1000, 10 power 4, 10 power 5. You can go up to any point as soon as you cover all the break frequencies, and this is our omega. And here we have minus 135, minus 180 degrees. Okay, so we know that one of the line is at, this is our origin, so we should draw, because we have 3 break frequencies, so our origin is this, but we have to draw a line also at this point, this straight point, because this is our origin. So whatever will be our origin, we have to draw a straight line at that origin, right? Now this is the total contribution of, if we have 3 zeros at origin and 2 poles at the origin, so we will, you know, if like S3 divided by S square, so these 3 corresponds to 270 degrees and this corresponds to minus 180 degrees, so our origin will then be 90 degree. So it's actually the added version of these 5 things, so it's basically the added value, right? So we have already added this graph, so we have to draw a straight line. This is the added contribution. So here we are dealing with only a single pole. In this transfer function of our question, we have only a single pole, so this is basically this one value, so that's why our origin is at minus 90 degree, right? So if it was this case, then it would have been plus 90 and we would have drawn a straight line at plus 90, right? Now the second break frequency is omega 1 is equals to 10, whose multiplicity is 2. So we just have to first find, okay, omega is equals to 10, so we have to find the previous decade, the start point and the end point. So the start point will be the previous decade, because 10 is here, this is my point, break frequency point, previous decade is this, so this will be my start point, this will be my end point, and we know that this is 0, this is a 0 with a multiplicity of 2, this is a 0 with a multiplicity of 2, so it must be plus 90 degree per decade. So the line will be straight up till we hit 1, not 10. Break frequency is 10, but it should start at the previous decade, and we should move 90 degree per decade. So one decade is from 1 to 10, so it should move 90 degrees. So we are standing at minus 90 degrees, so in one decade we should travel 90 degrees, mean we should reach 0 degrees, so we should reach this point in one decade, and then in the other decade we should reach from, we are at 0, so we should reach at 90 in this decade, so we should reach 90, and then it would flatten out, not like in the Bode magnitude plot that we should go onwards up till infinity. So this is the slope of the first break frequency. Now we have to consider the second break frequency, which is 10 power 4. So the second break frequency, which is 10 power 4, and we know that it's a pole and its multiplicity is 1, so it will be minus 45 degree per decade. Now its starting point will be the previous decade. 10 power 4 is here, so the previous decade is here, so its start point will be 1000 and its end point will be 10 power 5. So the line should remain 0 until we hit 1000, and after 1000 it should start moving minus 45 degree per decade. So the one decade will be from this point to this point, and we have to move minus 45 degrees in one decade. So in one decade we should reach, because we are standing at minus 90 at the moment, so minus 45, further minus 45 is at minus 135. So we have to reach this point in one decade, and then we have to reach this point in the other decade. So the starting point was 1000 and the end point was 10 power 5. So this is the contribution from the second corner frequency. So now, just like we did in the Bode magnitude plot, we have to add them graphically. So if we have to add them graphically, just replicate the same graph again and start adding it. So our origin was at minus 90 degree, then we have minus 45, then we have 0, then we have 45, then we have 90, then we have minus 135, then minus 180. Okay, and there was our 0 0.1, then 1, then 10, then 100, then 1000, and 10 power 4, 10 power 5. Okay, this is omega and this is degrees. So just start adding the lines. So our origin is at minus 90 degree, so we have to add only these two lines, because this was only for the origin. So don't, we have all, it was already the added version of these contributions, right? So we just have to add the slopes. So we have a single slope up till 1, we don't have any lines. Up till 1 we don't have any lines, so we should stay 0 up till 1. After 1 we have 90, we have 90 degree per decade. It was 90 degree per decade, it was minus 45 degree per decade. So at 1 a single line started up till 100, and there is no other line to add with this line, right? So it will be exactly the same. From 1 to 100 we have to draw a straight line of plus 90 degree per decade, and we know that it reaches 90. It reaches 90 when it reaches 100. So it reaches 90 when it reaches 100, and after this is it flattened out. After this it flattened out, right? And there is no other line to add up with. So we will go till this 1000 without anything. So we have no line here to add, we don't have anything here, right? So we should flatten the added graph as well, because there is nothing to add. We have to go straight till 1000. We have no lines in this region, and after this another line started which is minus 45 degrees per decade, and which start at 1000 and ends at 10 power 5, right? So at 1000 another line started which starts at 1000, okay, and which moves minus 45 degrees per decade. So minus 45 degree per decade means that from this 1000 to 10 power 4 it should decrease minus 45. So it is at 90 at the moment, it should reach 45, then it should reach 45 then, and then at 10 power 5 it should again decrease minus 45, so it should reach 0. And after we reach this 10 power 5, all the lines flattened out. Now there is no other line after this 10 power 5. This also flattened out, this also flattened out, this also flattened out. So the graph will be flattened out, right? So in this region we had 90 degree per decade, in this region we have minus 45 degree per decade. So that's the Bode phase plot. So this question ends here, but here is one complexity that I want to describe, which usually arise in some other questions. So let's say we have another frequency. So these questions end here. This is another discussions that I want to describe as well. So let's say we have another slope at 50, which ends at, let's say, you have any slope like this, it ends here, and we want to add, and this slope is also plus 90 degree per decade. It's just I want to explain this thing because it sometimes get complex. So now if we want to add these three curves, then we know that till 1 we have nothing, till 1 we have nothing, so we have to go straight till 1. Okay, after 1 we have a single slope of plus 90 degree per decade, but look at this, we have a single slope till 50, we have a single slope of plus 90 degree till 50. So till 50 we will go plus 90 degree per decade, but after 50, but after this 50 value we have two slopes, not one, we have now two slopes of 90 and 90. So it will becomes 180 degree per decade until this first slopes die down, and this first slope die down at 100. So till this point we have 90, so we have 90 from this and 90 from this. So it will be 180 degree per decade from 50 to 100. So from 50 to 100 it will be 180 degree per decade, right, in this region 180 degree per decade, and at 100 we know that this slope die down. So this die down, now from this 100 to 1000 we have only this one slope to deal with, we have only this one slope to deal with, which is 90 degree. So it will again become, so it will, let me just draw again, so it will be like, first it will be 90 degree per decade, then it 180 degree when these both combinedly, and then after the effect of first one finished it become again 90 degree per decade, and then at 1000, and then at this 1000, not this 1000 in fact, after this, yes, at this 1000 now we have 90 and minus 45. So we have two slopes to consider up till this point, right. So we have to do, one is 90, other is minus 45. So 90 minus 45 is minus 45. So the slope will then be minus 45, and then when we reach this point these all slopes die down, and now only this one is left, which is minus 45 degree per decade. So sorry, in fact this was 90 minus 45, so it was plus 45, not minus 45, it was plus 45, so it was plus 45. It was plus 45, and after this line ends we only have now one slope to deal with, which is minus 45. So it will be minus 45 until we reach this 10 power 5, then all the contribution will die down. So at 10 power 5 this will also flatten out. So it was just to explain this complex case. Let me just repeat it again because I think this is important to understand. So we want to add these three curves. We have one curve from this point to this point, we have another curve from this point to this point, and we have another curve from this point to this point. So I hope that you know how to draw all these individual curves. That was not difficult, but to add them graphically it's like a little bit complex. So till 1 we have nothing, so till 1 we have nothing, after 1 but till 50 we have plus 90 degree, after 1 but till 50 we have only one slope of plus 90 degree, but after 50, but till 100, because this slope now die down, you have to be very careful that which slope die down at which time. So this slope now die down after 100. So this is another region where there are two slopes of 90 and 90. So 90 plus 90 is 180 degree. So till 100 we will move 180 degree per decade, then from 100 to this 1000 we have only one slope to deal with, because the other started at this 1000, which is only plus 90 degree. So it will again decrease to plus 90 degree till 1000. It was again 90 degree per decade, and when it reach this 90 degrees, when it reach this 1000, now up till this point, let's say if it is 2000, up till this 2000 we have two slopes to deal with. One is 90 degree, other is minus 45 degrees. So the total contribution is plus 45. So up till 2000 it will move plus 45 degree per decade. Okay. At 2000 this contribution also die down. Now only one slope remains, which is minus 45 degree per decade. So the total contribution is minus 45 degree per decade. So we started moving at minus 45 degree per decade, and will not move up till infinity, but we should only move till 10 power 5, because after that all slopes die down. So minus 45, and at this 10 power 5 all slopes die down. So this is how we add them graphically. I hope you understand this basic concept that I have provided in the end. It's a little bit complex, but I hope you understand how to do it. So that's all from this video. If you have any question, you can ask in the comment section. Thank you.